Hi everyone, and welcome to a new video about noise analysis in op-amp circuits. This is our example number 3. In this example we'll look at another inverting amplifier as we did in the example number 2, but this time we have an inverting amplifier with a level shifting. So we will look at the performance in terms of noise for this circuit, and of course we will calculate the required values step by step and then verify this in our simulations using SPICE. So let's look at our example. What we have in this circuit, we have 4 resistors, R1, R2, R3 and R4, and we have an op-amp OPA 209. We have the input here, and these 2 resistors, R3 and R4, are equal 10 kilo ohms, as also shown here, and we have a battery of 5 volts here. So this is actually the part that will cause the level shifting. We have R2 and R1, which is then the gain part of our amplifier. So we have a gain and also the level shifting. That will be verified later on in more detail. Now, what is the question? Questions are the following. We would like to know the input referred RMS noise voltage and also the output referred RMS noise voltage. So those are the required calculations for this example. So let's look at our solutions. Of course, before we move on with the solutions, we need to work out and discuss the op-amp specifications in more detail. Now, from the datasheet of the OPA 209, you can find these 2 plots. And the left side is the input noise voltage spectral density, and the right side you can see the plot of the input noise current spectral density of this op-amp. Now you can see the op-amp has the noise voltage spectral density here on the right side on the y-axis as a function of the frequency, which is also valid for the input noise current spectral density as a function of the frequency. Now, in addition, you can see also these parameters. We will also use them to determine the input referred and the output referred RMS noise voltage for this circuit. So let's look at our example of the op-amp circuit and then in specific form what we require for our calculation. So we start with the DC open loop voltage gain, AOL, and that is 132 dBs, which is shown here. That is the open loop voltage gain, and you can see it's typical 132 dBs. The gain bandwidth product, which is a very important parameter, the gain bandwidth product is 18 megahertz, and it's actually shown here in the frequency response part, which is 18 megahertz. The broadband noise voltage spectral density, which is given by this symbol, small letter e sub NBB broadband, is 2.20 nanovolts per root hertz. That is shown here, so you can see also the unit, but that is also visible in this plot. So if you look at the plot here, which is then of course as a function of time, the first part is a different part that will be clarified shortly, but the second part actually, which is then a constant value, which is called the broadband or the white noise part, and that is approximately 2.2 also in the plot. So that's also verified from the table and also from the graph. You have also the broadband noise current density, and that is 500 femtoamps per root hertz, which is also shown here in the table, but that is also seen here in this graph. So you can see 0.5 picoamps, which means of course 500 femtoamps per root hertz. In addition, we have the first part, as I said before, that is the part where the input noise voltage spectral density will change as a function of frequency. So this part is called the 1 over F noise part, which is then in a specific case the 1 over F noise voltage density, and we will most of the time specify that at a specific frequency. In this case, it's the 0.1 hertz. So that is the symbol for that one, and that is then given by this value to 20 nanovolts per root hertz. You can also see that here, 0.1 hertz, and the value here is 20. So that's actually for this part. In a similar form for the noise current, so the 1 over F noise current spectral density at that 0.1 hertz, you will look at this table and you can see it is 3.75 picoamps per root hertz, and that's actually these are the important values we will use later on in our analysis. So let's continue and then look at the circuit performance in more detail. We have of course the gain of the circuit, which is the gain which amplifies the signal itself, but it also amplifies the the noise itself. So we have actually two gains. We have the closed loop gain, which is actually the closed loop signal gain, and we have the closed loop noise gain. So the SG and the NG, those are the values we require. Now this is an inverting amplifier. It has a level shifting, of course, but if you look only at the AC part, so AC perspective, you will have actually this formula again, which is minus R1 over R2. That will be minus 5000 over 1000. It will be minus 5 for our signal gain. The noise gain, as we discussed also in the previous examples, is always taken by definition from the non-inverting input of this op-amp. And in this case, since this will be disabled for noise analysis, that will be a short, and this will be also a short. So these two resistors will actually will be combined, and you have actually this source here, and then you will have your non-inverting amplifier formula, which is then 1 plus the feedback resistance divided by this resistance, which goes from the inverting node to ground, and that will be 1 plus 5000 over 1000 will be a 6. So your noise gain is different in magnitude than your signal gain. Okay, the bandwidth is also a very important one. We have two bandwidth. We have the signal bandwidth and we have the noise bandwidth. And this is important because we will use this value for our noise analysis. So the signal bandwidth can be calculated using the gain bandwidth product from the op-amp specifications from the datasheet. That was 18 megahertz and our noise gain was 6. So that's the formula. Signal bandwidth is equal to gain bandwidth product over noise gain, and you will have 3 megahertz. That will be our signal bandwidth. Now we have one op-amp, and there are no other active or reactive components. So we don't have any other op-amps, or we don't have any other transistors to have the system more than first stage or first order. So for this circuit, we can assume that it is a first order circuit, since this is just a just a one op-amp. And then for a first order circuit or first order system, we can use in the noise analysis the brick wall conversion factor. This is then the K sub n is then pi over 2. If you have, of course, a second order system, this will change. There are other values. You can also find it on the internet. But this is the value we will use for first order system. I won't drive this value. This is just what we use. Now we have then the noise bandwidth for the circuit then given by this expression, which is this noise bandwidth is equal to the signal bandwidth times this conversion factor. So we will have pi over 2 times that 3 megahertz. You will have 4.712 megahertz. This is, in this case, much larger than the signal bandwidth. Okay, now the next one is the total noise voltage. We have now the necessary values to go to the input referred RMS noise voltage and also the output referred RMS noise voltage, because these are the values we require from this example. Now, taking these together and using the noise gain for specific noise analysis, we will have the output noise RMS value of that one will be the noise gain times the input noise voltage in RMS value. So the input referred RMS noise voltage here is actually composed of 3 parts. The first one is the op-amp model, as you can see here. This is actually the model of this op-amp. We have the input current source of the op-amp and also the input noise source of the op-amp. And we have also the resistors around it. So we have actually 3 parts, which will of course then be determined by this noise current of the op-amp, noise voltage of the op-amp, and also the resistors, which will then contribute by a terminal noise. So in summary, we can say the input referred RMS noise voltage will be then due to the internal op-amp noise voltage sources combined in one source in this model, and that will be given by this symbol. We have also the input referred RMS noise voltage, then due to the internal op-amp noise current sources, and which is then given by just this symbol in our model. And we have the input referred RMS noise voltage due to the resistors, and that will be the effect of these 4 resistors, and that is just the terminal noise voltage. Now, if you combine these two and you will like to know what the effective input referred RMS noise voltage for this circuit is, then you will use the root sum of squares for these three parts. So you will actually have then the input referred RMS noise voltage is then the square root of the square of each part and then add them up. That is actually how we calculate this. So you will look at it in more detail, and let's keep it the model of this circuit of the op-amp and also the resistors around it. So let's first start with the first one. The input referred RMS noise voltage due to the internal op-amp noise voltage. So that is on its own also composed of two parts. We have seen in the datasheet that we have the 1/f noise part, which is dependent on the frequency, and also the independent part of the frequency. So that's actually why we have the broadband noise voltage in RMS and also the 1/f noise voltage and again in RMS. And these will be combined again in root sum of squares using this formula, very similar to what we had for the input referred RMS noise voltage. So the broadband noise voltage, we know that we can calculate that using the input noise voltage spectral density of the op-amp times the square root of that noise bandwidth. So we know the single bandwidth, which is 3 megahertz. We know then using the datasheet here, then the noise band will be then given by, again, the conversion factor times the signal band will be then the 4.712 megahertz. So if I now substitute the values, this is then E sub NBB, that is shown here, 2.20 nanovolts per root hertz. And also the square root of that noise bandwidth, you will get very close to 4.776 microvolts in RMS. That's actually for the first part, broadband noise voltage. For a 1/f noise voltage in RMS value, we will use this formula, and we need the normalized value of the noise voltage, and the parameters are here the following. We have the upper cutoff frequency, which is actually also the noise bandwidth in this part. We have the lower cutoff frequency or lower part of the frequency in this 1/f noise region, which is a selected frequency for the normalized 1/f noise voltage. So we will use, of course, for that a datasheet. And most of the time, the value of the FL is taken as 0.1 hertz. So we will have to use a selected value for our low frequency, low cutoff frequency FL. That is 0.1 hertz most of the time used, but any value will do here. So if you also look at the normalized voltage, noise voltage source or noise voltage value here, that will be used or calculated using this formula. So we have then the 20 nanovolts per root hertz, that will be of course determined by the datasheet. You will take then times the root of the 0.1 hertz, that's actually this formula, and that will be used in this RMS 1/f noise voltage. So if you do the math here for yourself, you will get, again, for FH, that will be, of course, the noise voltage, that will be 26.58 nanovolts RMS. And if you convert that to microvolts, that will be this value. And you can see already here that the contribution in the broadband noise is much larger than the 1/f noise. So that will be also seen later on in this final result for the contribution in this part. So you can then calculate the input referred RMS noise voltage due to the internal op-amp noise, and then using the formula here, as we also already said, in the root sum of squares. So if I now combine these two values, you will have then this result. And that is then the final value for this part, and you can see that this is then 4.776 microvolts RMS. That is exactly the same as the broadband noise voltage contribution. So the broadband noise voltage is dominant in this case. So let's look at the next one, which is then the input referred RMS noise current voltage due to the, this is actually the voltage due to the internal op-amp noise current. Now that is of course due to this part of the circuit. So we have the, you need to calculate the, for that one, the equivalent resistance, which is seen actually by the noise current source of the op-amp, which is an IN in this case with RMS value. So then the equivalent resistance will be then seen by this noise current source IN. And then we will use Ohm's law, which is just the input referred RMS noise voltage will be then the noise current source of the op-amp in RMS times this equivalent resistance. But on its own, this IN is composed of two parts, as we had also for the noise current part, which is in the broadband noise current, and also the 1/f noise current, both in RMS value. And then IN is then calculated using root sum of squares, using this formula again. So we need to again use this and then multiply that with the equivalent resistance. So let's then do the step by step, the broadband noise first. The broadband noise current, which is then given again by the similar expression. We take this from our datasheet, which is shown here, 500 femtoamps per root hertz, times the square root of the noise bandwidth, and I have the first, of course, the signal bandwidth, and then from there the noise bandwidth, which was 4.712 megahertz. If I do the math, I will get 1.085 nanoamps RMS. Now for the 1/f noise current, again in RMS value, is this formula, which is again similar to the 1/f noise voltage part. This is again the FH is the noise bandwidth, FL is a selected frequency normalized for the 1/f noise current, which is then for this part, and we will use the datasheet for that one, but most of the time you will select for FL 0.1 Hz, but any other value will do. So the normalized noise current then is given by this expression again, 3.75 picoamps per root hertz, which is shown here, also determined from our datasheet, times the square root of the 0.1 Hz. That will give you 1.186 picoamps RMS. Now we have the necessary parts for our calculation of the 1/f noise current, and that will be then the following results. So we have the 1.186 picoamps RMS times the square of this expression using the noise bandwidth and also the FL of 0.1 Hz. You will have 4.985 picoamps RMS. That is for the 1/f noise current in RMS value, and what you can see is the broadband noise current contribution is much larger than the 1/f noise current contribution, because it is in nanoamps, it is in picoamps. So if you convert this to picoamps, that will be 1085 picoamps RMS, which is much larger than that one. So that will be, of course, seen here in more detail. If you now use the RMS values of the broadband noise current and also the 1/f noise current together, you will have, using this formula, which is also shown here, then this value, which is then exactly the same as the broadband noise voltage noise current. So that means we have the dominating part is the broadband noise current part. So of course now we have the different situation, because we need to calculate the equivalent resistance for this current noise current source, and this part we see actually two branches by this noise current. That will be the R1 and R2 in parallel, because this is a short which is disabled, and this is also a disabled part. So we have actually R1 and R2 in parallel, but it also sees actually, since this is disabled, which is then short, and this is of course also disabled because we use superposition, we have the R3 and R4 also in parallel. So we actually two equivalent resistances, which is the first one is the R equivalent 1, which is the R1 in parallel with R2, and if you do the math here in this formula, you will get 833 ohms. For the second one, R3 and R4, you will have then 10,000 in parallel, 2,000 to 10,000 ohms in parallel, you will have 5 kilo ohms. So the expression now will be then the equivalent resistance in effective form will be then calculated using this formula. You can of course use the Ohm's law directly using this expression and then say, okay, the E sub Ni, which is then of course the input referred RMS noise voltage, this is a voltage of course, due to that internal op-amp noise current, can be calculated using this formula. But you can also say, if you want to do it in separate form, you can multiply that In, which is shown here, times each equivalent resistance and then square them each and add them up and then take the square root. That is also possible. So if you do the math in that similar form, you will have this one, and then the value will be 5.502 microvolts RMS. That is actually for this part. And again, the broadband noise current is here dominating. So the next part, the third part of our input referred RMS noise voltage, is then the input referred RMS noise voltage due to the resistors only, which is then given by this symbol. And that is calculated using the white noise or the thermal noise formula for the resistors. And of course we'll look at the equivalent resistors here. So the thermal noise voltage for the resistors is in general given by this expression, 4 kT times resistor in question, and then also the noise bandwidth, and then the square root of that one. Now, the K here is the Boltzmann's constant, which is this value. The T is the absolute temperature, and for room temperature operation, let's say 27 degrees operation, that will be 300 kelvins. The R, again, is the equivalent resistance seen at a node, and the noise bandwidth is then given here in hertz. Now, for this circuit, we have, again, two equivalent resistances. That is the first one, and that is the second one. We have discussed this in the analysis for the input noise current source of the op-amp, and we have the noise bandwidth here. Then we have the following situation for each case. So we have now the RMS or the thermal noise voltage due to this resistance, which is then just substituting the values in this formula. You will have 8.037 microvolts RMS. And if you do a similar calculation for the second equivalent resistance, just substitute the values, only this will change to 5 kilo ohms. You will have 19.69 microvolts RMS. So the final one is actually combine these together to have the effective or total input referred RMS noise voltage due to the resistors in total. That is then this, again, using the root sum of squares. So if you do math here, you will get 21.26 microvolts RMS. So we have the necessary elements now for each part, the resistors, the input noise current source of the op-amp, and also the input noise voltage source of the op-amp. Now we can combine them to get the total noise input reverse noise voltage in RMS. So the input referred RMS noise voltage of this circuit, again using root sum of squares, will be then, of course, using this formula calculated, and then we have already calculated the input referred RMS noise voltage due to the input noise voltage source of the op-amp is given by this value, and for the noise current contribution at the input was this, and for the thermal noise voltages it was 21.26. So that's actually the major contribution in this case. So if you combine them together, again using this formula, just substitute in here, you will get 22.48 microvolts. And you can already see that the thermal noise due to the resistors is actually dominating here, because the 21.26 microvolt RMS and this one, the actual value doesn't really differ a lot. So this is really dominating, which is then the thermal noise voltage due to the resistors. Now we also need to, of course, this is just the input referred RMS noise voltage, and we will look also at the total output referred RMS noise voltage. So the total output noise RMS voltage at the output will be then calculated using the closed loop noise gain. In this case, the NG was 6, because we look at this non-inverting amplifier and then calculate the magnitude or the gain using this noise source only. Now the input referred RMS noise voltage, we already have this, and then using the output referred RMS noise voltage, then this expression will be then calculated using this formula. So we have the noise gain times the input referred RMS noise voltage will give us output referred RMS noise voltage. Now if you do the math, you will get 6 times this, you will have then the 134.9 microvolts RMS, which is approximately 135 microvolts RMS. So that is all result, and this is then the input referred RMS noise voltage, and this is then the output referred RMS noises. Of course we will verify this, but let's also look at a very important aspect, which is the signal to noise ratio, SNR. Now briefly recap, which is then the signal to noise ratio is a measure that compares the desired signal level to the noise level. So we have a comparison, and in the precise definition is actually the ratio between the signal power and the noise power, and that is often expressed in decibels and dBs. So it is a ratio, so if your ratio is larger than 1, for the SNR, that means greater than 0 dBs, it indicates that you have more signal to noise, which is good. But if you have a ratio which is between 0 and 1, which is then smaller than 0 dB, which is then a negative value, that indicates you have less signal than noise, or you have more noise than signal, which is then of course not what we want. What we want is of course to optimize or increase the signal to noise ratio to higher values. Now for this circuit, the SNR at the output for a specific frequency can be calculated using this formula. And we know already what our output referred RMS noise voltage is. So if you do the math here, just calculate it, you will get 77.4 dBs. That's what we have for our SNS and SNR. So that will also be verified in our simulation. So let's look at the simulation results. First, we start with a frequency response, and then specifically we also look at the bandwidth of this circuit. Now this is our circuit with the model, and we can see in this plot that we have a DC gain of approximately 14 dBs, so this is 13.979. We have a cutoff frequency of 2.966 megahertz, and we have some labels here to indicate that this circuit is behaving as a first order system. But let's start with the first one, which is a DC gain. We have here approximately 13.89 dBs, and if you now convert this dB expression for the DC gain in a scalar form, you will have very close to 5, and that is a confirmation that our signal gain is correct also in the simulations. The cutoff frequency I've calculated already, that was 3 megahertz, and we see that this is 2.966 megahertz, which is very close to what we have calculated. So that result is also very nice. We also need to check that our assumption of a first order system is valid. What we need to do is just look at several values in our plot. For example, at 10 megahertz, I see it is approximately 3.06 dBs. Now to have a first order system, this line needs a decrease of 20 dB per decade. So the slope must be here minus 20 dB per decade. If I increase this frequency, so 10 times, so 1 decade up, that will be 100 megahertz, and I need to go down by 20 dB. So it is 3.06 dBs, and that must be then minus 16.06 dB. It is very close to that. One is a little bit larger, so it's very close to what we actually require. If I also check another decade increase, so to 100 megahertz to 1 gigahertz, so it is then 10,000 megahertz. This must be, of course, also have a difference of 20 dB, and you can see this difference is also very close to 20 dB. So in approximation form, this is very close to a first order system. So let's also look at the input noise voltage spectral density. This is done this plot. You will again recognize the first part, which is then the 1 over f noise part, which is dependent on the frequency, and the second part, which is then independent of the frequency. So you can see this will stay at a value no matter what you do with the frequency, and this part will definitely change due to the frequency. You also see the final part here, which is then decreasing. That is actually due to the modeling of our noise, which is of course not perfect. So we have the frequency dependent part, which is the 1 over f noise, which is this part, and the independent part, frequency independent part, which is the broadband or the white noise part of this circuit. Now we have also the output noise voltage spectral density, which is of course will be resulted due to the input noise voltage spectral density. This is in this plot. You can see directly that it is much larger because we have a noise gain of 6. Again, we have a 1 over f noise part, we have the broadband part, and we have a different part which will then approach to 0 value for the noise. So what we have is a frequency dependent part, 1 over f noise again. We have the frequency independent part, which is then the broadband noise or the white noise part. But we have also that part that goes to 0, that is due to the bandwidth limit of the op-amp. Because if you look at the input, there is no bandwidth limitation in theory. But this op-amp will of course bandwidth the signal which goes in the op-amp and then of course approach the output. So we will have the output noise goes to 0 if you of course increase your frequency, because due to that the cutoff frequency of your op-amp itself and also the resistors around it. So that is why we have this curve approaching 0 for the output noise spectral density. Okay, the important part again is the total RMS output noise voltage. That is in the output. What you see is again our circuit with our model, and we have integrated this simulation up to 1 gigahertz. You can see the value here. We had calculated 134.9 microvolts RMS. That's our calculation for the total RMS output noise voltage, and the simulation says 135.6 microvolts RMS. So the difference in here is just 0.7 microvolts RMS approximately. So that is a really nice result in terms of percentage. So that is a confirmation again that the calculations do match very well with the simulations. Let's also look at the signal to noise ratio. This is the plot. You can see the signal to noise ratio here on the y-axis and also the frequency in the x and the horizontal axis. The signal to noise ratio starts off very large and then it decreases and then has a slope which is a constant slope in the log scale, and then approaches again some steady value at approximately 77.4 dBs. We had calculated using this formula, the SNR, and this value for our output referred RMS noise voltage. We had calculated SNR was 77.4 dBs, but if I look at the simulation, it is 77.36 dBs. And this is a very nice match that this is, again, the SNR and the simulation and the calculations do match very well. So, of course, again, it of course depends on the frequency, but if you look at the frequency in the long term, the SNR will be very close to what we have calculated, and that is a nice confirmation of our calculations. We also look at the SPICE itself and the SPICE simulator and also see how we can generate these plots. So let's then now jump to SPICE simulator. So we are in our SPICE simulator. This is our circuit. I have already prepared the circuit for you. We have the 4 resistors, the battery, and our input AC voltage. We have the 2 noise sources for this op-amp and the op-amp itself and the power supplies, and we have the output measuring point here. Of course, we are interested in the noise analysis, so what we do is we go to analysis, noise analysis, and we have then the possibility to start at the for frequency at, for example, 0.1 Hertz, or you can also do 1 Hertz. That depends on what you prefer. So I will just use 0.1 Hertz, and I go up to 1 gigahertz, and this is the number of points to make your accurate plot. So I find out that this is actually the maximum what you can get in this simulator, and you can now also select several diagrams. So we have the output noise, which is then output noise spectral density. You have the input noise, which is then the input noise spectral density, to the total noise, which is then the total noise RMS voltage. So that's actually the RMS value of your output noise, and you have the signal to noise ratio, which is then at the output. Let's run this and then see what we get for our graph. So this is then now prepared in the calculation. Okay. Now we have now prepared the plots, so I can of course place them here. Maybe I may just make it full screen. This is then the output noise spectral density. You can see it is a 1/f noise part, the broadband part, and also it approaches to 0 value for higher frequencies because the frequency limiting of the op-amp itself. I can also go to the input noise spectral density. Again, it starts off very large, but it has a frequency dependence part, which is then do that 1/f noise part, and then it has a constant value, and this part, which is then going down, is due to that inaccurate modeling of the noise of the op-amp. Now, important part is of course the total RMS noise voltage. You can see it starts off small, or 0 actually, very, very small, and then goes to a value and increases actually because this is just integration of the noise spectral density at the output for frequencies, and then you will approach approximately 135.6 microvolts RMS. And it's actually very close to what we have calculated. There's also the discussion in our analysis before we jump to this part. Now we have also the signal to noise ratio. It starts off very large and then goes down, and it has a slope which is constant in a log scale. And you can also see that the signal noise ratio will approach a value which is then 77.36 dBs approximately, and at approximately 1 gigahertz. So that's actually again the way how to generate these plots: the signal to noise ratio, the output noise voltage spectral density, input noise voltage spectral density, and also the total RMS noise voltage at the output. So that's our third example about the circuit we have with the inverting amplifier having a level shifting, in this case due to that R3, R4, and we have that 5 volts, and that will cause of course a level shifting here. But you can see that the resistors do have effect of the performance of your noise. Okay, thanks again for your attention. I hope this clarifies the situation even more in detail for this inverting amplifier with a different addition, which is the level shifting in this case. Of course, we will look at different configurations and circuits in next examples. If you have any questions, comments, please let me know, and I will try to answer them as soon as possible. Thanks again, and see you next time.